Okay, I'm going to do a video on points of concurrency in triangles. I'm going to use this graphic organizer that'll really help you remember what the different special types of segments are, as well as visually see what intersection and points of concurrency. Now, just real quick for your own definition, you might want to write this down. A point of concurrency is where three or more segments intersect at the same place. So that's that point that three or more segments intersect. So point of concurrency, all three special segments, say all three medians of a triangle or all three perpendicular bisectors of a triangle, they all intersect at the same point. That point is called a point of concurrency, and they have a specific name depending on the type of segments that intersect. So we're going to just go right down the line from left to right here and talk about circumcenters. So a circumcenter is the intersection, and you could take a look at this picture here, and I'm going to zoom a little bit so you can kind of focus on it. And you can see that these are perpendicular bisectors. Now notice that they're not necessarily connecting an angle to the opposite side. What's important is that, say, ZM is the perpendicular bisector of AC. So it doesn't have anything to do with that opposite angle. It just is going, it's a perpendicular line through the midpoint Z. So super important that you see the right angle mark for perpendicular and then the congruent marks on either side of Z to indicate that Z was the midpoint because AC was bisected. All right, so the circumcenter is the intersection of the perpendicular bisectors. So here we go, got it filled in for you. The intersection of the perpendicular bisectors is what creates the circumcenter. And the circumcenter, important fact here, now this is one of the things that you're going to have to commit to memory, is that the circumcenter is equidistant from the vertex of, is equidistant from each vertex of the triangle. So it's equidistant from the angles. So that point M right here is the same distance from A as it is from C as it is from B. So it's equidistant from the angles of a triangle. The circumcenter, which is, again, created by the intersection of the perpendicular bisectors. Okay? Next is the incenter, and the incenter is created by the intersection of the angle bisectors. So the incenter is the intersection of the angle bisectors. So that's the line segment that cuts an angle into two congruent pieces. So you can see here that BM bisects angle B, AM bisects angle A, and CM bisects angle C. And what's important is that the incenter is equidistant from the sides of the triangle. So the circumcenter was equidistant from the angles. Now the incenter is equidistant from the sides. So just something to pay attention to. These distances here, and I'm going to try to do that a little bit better for you. These distances here indicate the shortest distance, which is the perpendicular distance from a point to a segment. So that distance, and that distance are all the exact same length. So the incenter is equidistant from each side of the triangle. That means that M to X is the same as M to Z is the same as M to Y. Now, really important that you notice is that those right angle marks indicate that the distance from M to Y is the shortest distance that you can draw from M to that line segment BC, from M to that line segment BA, and M to that line segment AC. These perpendicular distances indicate that that's the shortest distance. So again, the intersection of the angle bisectors is the incenter, and it is equidistant from the sides of the triangle. Our next point of concurrency is the centroid. This is the intersection of the medians. Remember, a median goes from an angle to the opposite side's midpoint. So that means that in this picture here, X, Z, and Y are all midpoints. So M is the centroid because it's where those three medians intersect. Now, the medians, again, you think middle, and they are connecting a midpoint to the opposite angle. But an interesting thing about the centroid is it separates the median into a 2-to-1 ratio, meaning there's a larger part that's twice as big as the smaller part. So it's not the midpoint of the medians. It'd be nice if it was, but it's not. However, it does separate all medians into the same ratio. The big part is twice as big as the little part. So let me show you what I mean here. In this picture, BM, the length of B to M, is twice as big as the length of Z to M. So you would need to multiply the length of Z to M by 2 to make it equal to the length of BM. So let's say BM was 4, ZM would be half of that, or 2. And you would need 2 times 2 to get 4 for the length of BM. So keep in mind that the centroid is the intersection of the medians, and it separates each median into a 2-to-1 ratio. Our last point of concurrency is the orthocenter, and it's the intersection of the altitudes. So remember that an altitude is the height of a triangle, or it's the perpendicular distance from an angle to the opposite side. So notice these right angles indicate that perpendicular. So X, nor Z, nor Y are midpoints. They're not. They're just where that segment would be drawn from C to the segment BA, indicating that perpendicular distance or the height of that triangle. So the intersection of the altitudes is the orthocenter. There's nothing really special about as far as figuring out the orthocenter. The orthocenter doesn't have a relationship with the angles or the sides or anything like that, so there's nothing you have to memorize with that. But just know that the orthocenter is created by the intersection of the altitudes. Okay, we're going to do an example here. So if you take a look at this picture real quick, the markings on the picture tell you everything you need to know about that point M and its role in this triangle ADB. So right away, I start looking at it, and these marks here, these marks here, and these marks here indicate that I've got a series of midpoints. So C, H, and K are all midpoints according to the markings on the sides of the triangle. Well, that means that AC, DH, and BK are all medians because they connect an angle to the opposite side's midpoint. So then that would mean, and you should pick this up, that M is the centroid of triangle ADB. And as soon as you know that it's the centroid, then that tells you right away that the point M separates each of those medians into a 2-to-1 ratio. So AM is 2 times CM, DM is 2 times HM, and BM is twice as big as KM. So that's what should pop into your head right away once you determine that M was the centroid. So how's that going to help us in this problem? Well, they tell us that AC is 3x plus 2, and they tell me that CM is 4. Okay, well, I know that CM is 4. Well, automatically that should tell me that AM is 8. Well, if I add AM plus CM, that's going to give me 8 plus 4, which is 12. Well, that tells me that AC is 12. Well, now that's all I need to figure out my equation to solve for x. So 3x plus 2, which is AC, is equal to 12, which we just figured out the length of is. And now I'm just going to solve. Subtract 2 from both sides. 3x is equal to 10. Divide both sides by 3. And x is equal to 3 1/3, or 3.3333, repeating. Okay, our next example is this triangle HJI with W as that point of concurrency. So you take a look here and you see right angle marks, which makes you immediately think either a perpendicular bisector or an altitude. Those are our two things that have perpendicular relationships with the side of a triangle. And then these marks here, 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 and here indicate that those sides have been bisected because those segments are congruent. All right, so really important for you to understand here is that is the intersection, W is the intersection of the perpendicular bisectors, which makes W is the circumcenter of triangle HJI. Now, it's the circumcenter because it's the intersection of the perpendicular bisectors, but then what pops into your head is that the circumcenter is equidistant from the angles of the triangle. So that means WJ is the same as WI is the same as WH. All those distances from the circumcenter to the angles are the exact same. Okay, well then I go and look at this problem. HW, they tell me, is 2x plus 4. So there's no segment in this picture that tells you what that is. You've got to know that the distance from H to W is the same as the distance from J to W is the same as the distance from I to W so that you can set up an equation. So HW and JW are the exact same thing because they're distances from an angle to the circumcenter. So I can actually set those two things equal to each other and help me find X. Then they want me to find what IW is. Well, IW is the same as JW is the same as HW. So once I know what X is, I can plug it back into either one of those, HW or JW, and that number will be what IW actually is. So let's do that really quickly. All right, so we know that HW is the same as JW because the circumcenter is equidistant from the angles. So that means 2x plus 4 is 3x minus 2. So I'm going to just go ahead and solve this. Add 2 to both sides. And that's going to give me 2x plus 6 is equal to 3x. Subtract 2x from both sides. And 6 is equal to x. Now that's not my answer, but that is going to help me find my answer. Remember that HW, JW, and IW are all the same. So I'm just going to substitute 6 in for x for HW. So that means 2 times 6 plus 4. 12 plus 4 is 16. Double checking that we did that right. 3 times 6 minus 2 should be equal to 16 as well. 3 times 6 is 18. Minus 2 is 16. So you can see that our work checks out and that IW is indeed 16. So here's our final example with our points of concurrency. So right away you should recognize that ED, CP, and MT are all angle bisectors because they're cutting these angles, angle E, angle C, and angle M, into congruent parts. So what that would then mean is that W is an in-center, so it's equidistant from the sides of the triangle. So these right angles indicate that that's perpendicular distance from W to that side. So W to D is the shortest distance from W to CM, WT is the shortest distance from W to CE, and WP is the shortest distance from W to EM. All right, so those distances should all be the same, WT, WP, and WD, if indeed W is the end center. So what that then allows us to be able to do with this given information up here is to be able to set WT and WP equal to each other. That'll help me find K. And then because DW is the same as WT and WP, I can just plug K back into any one of those individuals and that'll give me the length of DW. So here we go. 5K plus 5 is equal to 8K minus 10. Subtract 5K from both sides. 5 is equal to 3K minus 10. Add 10. 15 is equal to 3K. Divide everything by 3. And 5 is equal to K. So that means everywhere I see a K, I could put a 5. And again, WT, WP, and DW are all the exact same thing. So I'll just plug it in for WT. 5 times 5 plus 5. So 25 plus 5 is 30. And that's what the length of DW would have to be since all of those are the same.